Carbon is a unique element in that in the periodic table, in that it forms bonds with itself.
But not all carbon is the same.
Carbon as an element can form inorganic materials such as carbon dioxide. So also contributes to the diversity of life.
Although not particularly abundant in the Earth's rocky crust, the element carbon does play a vital role in the presence and evolution of all life on Earth. Starting with some of the smallest molecules, such as proteins and amino acids, up through bacteria, plants, and animals, all life forms, and therefore all organic matter, is made from carbon. It exists in environments both on land and at sea. It presents itself in the grass at our feet and in the food that we eat. However, carbon seldom remains in one place very long. It continuously breaks down and takes new forms as it is renewed through the process of the carbon cycle.
So when we're studying dissolved organic matter, we're a very narrow slice of the pie on this path from carbon coming from CO2 through photosynthesis and through subsequent utilization and degradation by other organisms down the line back up to CO2. That's the carbon, that's the link between the organic carbon world that we know in soil and plants and the inorganic carbon world, which is the CO2 in the atmosphere.
Well, so what do? We go out, we look at carbon that's dissolved in aquatic systems in a whole bunch of different ways. Sometimes we go out and we grab a sample of the water and we take it back to the laboratory, and we might do simple characterizations such as put it in a spectrophotometer and look at how much light is attenuated as it's passed through the sample. Or we might look at the fluorescence properties of that organic material, and that gives us some information about the constituents, the chemicals that make up that aquatic carbon that's in the sample.
Organic carbon is highly reactive with other substances, and it is often tied up in a variety of reactions in nature. For example, in aquatic environments, this may include aiding the transport of toxic materials or pollutants by binding with pesticides or other toxic metals such as mercury. It is this ability to bind with other compounds that can facilitate the transport of these dangerous materials and can foster the uptake of these toxic materials by other organisms.
In particular, one of the major societal issues that we're working on is the way in which dissolved organic matter controls the biogeochemistry of mercury. And mercury is a very interesting element in that in some of its forms is a powerful neurotoxin, and so when it gets into the food web and gets into the higher parts of the food web, such as game fish, we're then susceptible, when we eat those fish, to accumulate mercury ourselves.
Besides mercury, another reaction of organic carbon observed in aquatic environments relates to something most people use every day: municipal supplies of drinking water.
Drinking water treatment plants grab water from lakes or rivers, and that's got some of this dissolved organic carbon in it. And then they use powerful techniques, chemical techniques, for disinfection. So they put in chemicals such as chlorine, and the chlorine reacts with the dissolved organic matter to form these chemical byproducts called disinfection byproducts that are toxic, and they're regulated by the EPA in finished drinking water because they're unsafe for human consumption above a certain level.
Knowing what forms in the water is only a part of the story. Being able to measure and monitor changes to the environment is just as important.
One of the coolest things about studying carbon, organic carbon in lakes and rivers and in the ocean, is that carbon tells a story. It tells a story about where it's come from, what's happened to it along the way, and what its likely environmental fate is. And what's really neat lately is we've been developing sensors that you can go out and stick in the water, and you can measure the variation in the amount of that stuff that's there, but the quality of that stuff. And this is a whole brave new world in organic geochemistry, because we can figure out how our watersheds are functioning and how the river ecology is functioning on the fly in real time, and we can broadcast that up on the web.
The insights that USGS research chemists gain from studying carbon help guide policies that affect the health and safety for people and the world around us.
We all, in our daily lives, understand, in a maybe not a direct way, but the example I like to use is that if you head off to buy coffee in the morning and you're in desperate need of caffeine, and you get a cup of decaf, it's one molecule that makes the difference between your falling asleep at your desk or being wide awake. So our job is to understand the reactivity of individual molecules and how they are controlling critical processes on the planet.
Want to learn more? Additional information on how the USGS studies organic carbon, as well as its interaction with other compounds and pollutants, can be found online. If you are interested in other USGS research, you can follow the USGS Daily on Twitter, Facebook, or YouTube.
This podcast is a product of the U.S. Geological Survey, Department of the Interior.